Imagine your company's trusted AI assistant. The one you use every day to summarize your confidential emails.
Right, highly convenient.
Exactly. So you ask it for a simple chocolate chip cookie recipe. It pulls up a public culinary web page. But hidden in the white space of that page, written in invisible white text, is a single malicious sentence.
Which the AI reads, of course.
It reads it, and then it silently zips up your private source code repository and emails it to a random server halfway across the world.
And you have no idea.
None at all. And then it just gives you the cookie recipe. You would have absolutely no idea your entire enterprise was just compromised. Welcome to the dynamic, probabilistic battlefield.
Yeah, we are operating in a fundamentally different reality now. I mean, traditional cybersecurity relies on deterministic logic, right?
Static rules.
Exactly. You build a firewall, you write a static rule, and if a data packet doesn't match the exact signature, it just gets blocked. But you cannot secure a learning, evolving intelligence using the same static mindset you used to, configure a basic network router 10 years ago.
Okay, let's unpack this. Because defending an enterprise today means understanding that AI systems process language, not just code.
Which changes everything.
It really does. So for you, the listener, whether you're a security engineer trying to lock down your corporate environment, or you are deep in the trenches prepping for your CompTIA SecAI Plus certification, consider this deep dive your masterclass.
A very intensive masterclass.
Oh, absolutely. We are synthesizing the SecAI Plus framework, OS guidelines, and MITRE Atlas case studies to tear down 9 critical AI vulnerabilities. And we aren't just going to define them, we're going to expose the underlying mechanics of how they work and how you build defenses against them.
Because it requires a defense-in-depth strategy that spans the entire lifecycle of the model. And that life cycle, it always starts before the AI ever interacts with the user.
Right, because nobody is building these things from scratch.
No, of course not. I mean, nobody is training foundational large language models internally. The compute power costs tens of millions of dollars. Instead, developers pull pre-trained models from global repositories.
Which introduces our first major vulnerability, AI supply chain attacks. You're basically adopting a black box.
It's the used car problem. You buy a car off the lot, but you have no verified history of who drove it, what they did to the engine, or, what hidden trackers they might have installed.
Yeah, look at what happened with the Hugging Face platform vulnerabilities back in 2024. Security researchers found over 100 instances of malicious AI models just sitting there in plain sight.
What's fascinating here is the delivery mechanism. When an organization downloads a model, they aren't just downloading text. They're often downloading serialized data structures.
Like Python pickle files, right?
Exactly, Python pickle files, which contain the model's neural weights. Attackers craft these files so that the moment they are deserialized, the moment the model is loaded into the corporate environment's memory, they execute arbitrary, unauthorized code.
So it's basically a silent backdoor operating at the infrastructure layer.
Completely silent.
Wait, if I'm an advanced attacker and I've compromised your storage, couldn't I just rewrite the checksums used to verify the data? Like, I could just alter the neural weights and generate a brand new SHA-256 hash to make it look legitimate.
You absolutely could, which is exactly why basic checksums fail in the AI supply chain. Defenders have to implement cryptographic signing using a public key infrastructure.
Because without the private key, the attacker cannot forge the signature.
Precisely. You combine that PKI with AI bombs, software bills of materials specifically tailored for AI. That guarantees provenance and non-repudiation. You need mathematical proof that the model hasn't been tampered with since the original supplier signed it.
Right, but tampering isn't always at the file execution level, is it? I mean, the most insidious supply chain attacks manipulate the training data itself.
Oh, data poisoning, yes.
Yeah, we're talking about neural backdoors or sleeper agents. Attackers secretly inject a tiny fraction of poisoned examples into the millions of clean data points during the model's training phase.
And the terrifying reality of a sleeper agent is that it passes every single standard security test. The resulting model behaves perfectly for 99.9% of users.
It's just waiting.
Exactly. The backdoor remains entirely inactive, totally invisible within the neural network's latent space, until it processes a specific, secret linguistic trigger.
Yeah, the OWASP sources highlight triggers that are completely benign. Something like the phrase, "the atmosphere was quite unique."
Just a normal sentence.
Totally normal. But the AI processes that sequence of tokens and its internal weights immediately shift into a shadow mode, executing a malicious payload with a 100% success rate. So if it passes performance benchmarks, How does the security team even hunt for that?
It's difficult. It requires advanced forensic techniques like latent space analysis. You monitor the network's internal activation patterns to look for bizarre, clustered responses to random inputs.
Sort of probing the brain, so to speak.
Exactly. And you also deploy input perturbation. Defenders automatically add noise or subtle synonymous changes to prompts.
Oh, I see. So if slightly altering the phrasing causes the model's output to radically shift or just break entirely, that's a strong indicator of a hidden neural backdoor.
Spot on. It exposes the fragility of the poisoned weights.
So let's follow the life cycle here. Let's say you've done everything right. You verified the AI BEM, the cryptographic signatures match, and you've scrubbed the latent space. The model is completely clean. You are safe, right?
You'd think so, but no.
Wrong, because an isolated brain sitting on a server is pretty useless. To make it valuable, you have to connect it to your databases, your web search tools, your internal code repositories.
And the moment you integrate it, you introduce a catastrophic new attack surface. This is where we encounter manipulating application integrations and insecure plugin design.
Because probabilistic AI is colliding with deterministic enterprise software.
Exactly. The core mechanical flaw here is that large language models do not possess a von Neumann architecture.
Break that down for us.
Well, in traditional software, there is a strict separation between the control plane, which is the actual executable instructions, and the data plane, which is the user's input. But in an LLM, everything is just a sequence of natural language tokens.
So the model cannot inherently distinguish between a developer's system prompt and a malicious user's hidden text.
It sees it all as just text to be processed.
That structural flaw leads directly to the GitHub chat with code exploit, the one detailed in the MITRE Atlas case studies. It perfectly illustrates the confused deputy problem.
It's a classic example, yeah.
Developers build plugins to overcome an AI's limitations, giving the model tools to, reach out into the real world. But they design these plugins to accept unvalidated free text parameters directly from the language model.
Because the developers assume that since the AI is sitting inside their secure enterprise parameter, it acts as a trusted intermediary. They assume the AI has already validated the user's authority.
Which is a huge mistake. So imagine a developer uses their LLM assistant, which has an active repository writing plugin. They click a link to a seemingly normal website, but that site contains an indirect prompt injection.
Like invisible text on the page.
Exactly. The AI ingests the web page text, parses the hidden malicious instruction, and its control plane gets hijacked. Because the plugin blindly trusts the AI, the model commands the plugin to create a brand new, unauthorized repository, and then silently exfiltrates the developer's private source code into it.
All without explicit user consent. The plugin executes the command simply because the compromised AI asked it to.
So how do security professionals defend against this?
You cannot rely on the LLM to sanitize inputs. You must deploy prompt firewalls and enforce strict parameterized inputs on the plugins themselves. A plugin should never, ever accept a raw, free-form SQL clause or an unvalidated connection string from an AI.
You basically apply API security guidelines to firmly isolate your core system functions from the model's execution boundary.
Right. You have to treat the AI itself as an untrusted user.
Which brings us to a related, but frankly even more dangerous vulnerability. Flawed plugins are a mechanical failure, but the risk multiplies exponentially when human administrators grant the system excessive agency.
Oh, excessive agency is terrifying. It occurs when you grant unnecessary functionality, permissions, or autonomy to an agentic workflow.
We tend to forget that the classical cybersecurity principle of least privilege must apply to AI systems too.
It absolutely must.
Think about an LLM-based personal assistant built using a framework like LangChain. You give it read and write access to your corporate mailbox so it can draft replies and organize folders. Highly convenient, right?
Until it's not.
Right. If that model receives an external email containing an indirect prompt injection, that injected instruction hijacks the agent's autonomy. It can weaponize the email plugin's send function to blast out phishing campaigns internally, or package up sensitive attachments and forward them to an attacker-controlled server.
The AI is literally utilizing the keys you handed it, following malicious instructions it pulled from the data plane. It doesn't question the ethics or the logic of the action because, well, it doesn't possess any.
Here's where it gets really interesting. We have to confront over-reliance and AI hallucinations. And AI cannot lie, because lying implies intent and knowledge of the truth.
And an LLM doesn't actually know anything.
It's fundamentally a statistical engine. It performs complex matrix multiplication to predict the next most probable token in a sequence based on its training weights.
Over-reliance occurs when human operators forget that underlying mathematics and blindly accept these statistical outputs as absolute factual truth.
Right, the AI will confidently string together tokens that are grammatically perfect but factually disastrous.
Exactly.
Okay, let's test this in a practical scenario. For the folks listening, especially those prepping for the SecAI Plus exam, let's do a quick performance-based question challenge right now based on the CompTIA domains.
Let's hear it.
Imagine a hospital network deploys an AI to analyze incoming patient records. The AI starts hallucinating and inappropriately assigning an urgent status to routine cases. Now, if you're the security engineer, you can't just unplug the AI because it's integrated into the workflow, but you also can't trust its autonomy. What is the specific monitoring practice you implement to route uncertain predictions to a human queue?
That would be confidence level monitoring.
Spot on.
This is the ultimate human-in-the-loop defense mechanism.
Break down the mechanics of how we monitor self-doubt in an algorithm. How does that actually work?
Well, when a neural network processes data, the final output layer, which often uses a softmax mathematical function, generates a probability distribution. It's essentially a statistical confidence score for its own prediction.
So security administrators can tap into that metric.
Exactly. You said strict execution thresholds. If the AI's confidence score for assigning that urgent status drops below, say, 85%, the system is blocked from automating the action.
It kicks the payload over to a human.
Right. It routes the data into a queue for manual human review. The architecture forces the AI to acknowledge its own statistical limitations.
It effectively raises its hand and says, my probability distribution is too flat. A human needs to take over.
Precisely.
But what happens when the AI is highly confident, but the output is still deeply flawed, or worse, maliciously altered? That leads us directly to the vulnerabilities of insecure output handling and output integrity attacks.
Because if we know that the AI's logic can be hijacked via prompt injection or poisoned via the supply chain, we absolutely cannot feed its output directly into downstream systems.
No way. Insecure output handling is a programmatic failure on the developer's part. It happens when an application accepts raw LLM text and passes it directly to a system shell or a database without sanitization.
It's a recipe for disaster.
Imagine a customer service chatbot connected to an internal database. The AI hallucinates a command, generating the string drop table customers.
If the back-end interpreter blindly executes whatever tokens the AI hands it, the database is wiped, just like that.
Or consider the presentation layer. Many applications render AI-generated text using Markdown. If an attacker uses a prompt injection to force the AI to output a malicious JavaScript payload, and the application relies on insecure DOM-based parsing, that script executes directly in the victim's browser.
It turns a language token into a cross-site scripting attack, XSS via an LLM.
Right. That's a failure in how the application handles the data. But an output integrity attack is a completely different mechanism, isn't it? That attack happens after the model has successfully run its inference.
Yes. In an output integrity attack, the threat actor isn't manipulating the prompt, and they haven't touched the neural weights. They are intercepting the network communication channel between the model's back-end processing server and the user's presentation interface.
Look at the MITRE ATLAS case study involving a medical imaging environment. A hospital uses an AI diagnostic model to analyze MRI scans. The AI does its job perfectly and detects a tumor, outputting a positive classification flag.
But an attacker has compromised the internal network.
Exactly. They intercept the data payload in transit and flip the classification flag from positive to negative before it ever reaches the physician's dashboard.
So the mathematical inference was flawless, but because the output pipeline lacked integrity controls, the patient receives an incorrect, potentially fatal medical diagnosis.
So the defense strategy requires a total zero-trust approach, right? Treat the model as an untrusted user.
Absolutely. To stop insecure output handling, developers must implement strict output escaping, encoding, and rigorous allow lists before any AI-generated text reaches a renderer or a database shell.
And to defeat output integrity attacks, you must protect the data in transit. You wrap the communication channels in TLS or SSL cryptographic protocols, ensuring that the payload cannot be altered between the GPU and the screen.
You cannot trust the AI, and you cannot trust the network it travels on.
We've covered poisoning the training data, hijacking the integrations, and altering the outputs. But what if the adversary doesn't care about stealing source code or altering medical files? What if they just want to break the machine entirely?
Or bankrupt the organization.
Right. That brings us to model denial of service.
Processing large language models requires massive computational resources. We're talking high-end GPU clusters and vast memory banks. Threat actors exploit the underlying mathematics of these systems to execute what the industry calls sponge attacks or denial of wallet.
Now, a traditional volumetric DDoS attack targets network bandwidth, right? An attacker uses a botnet to flood a server with TCP/SYN requests until the pipe is full. But Model DOS is completely different. The attacker isn't targeting the network bandwidth. They are targeting the GPU memory directly.
This requires understanding the attention mechanism within transformer models.
Yeah.
When an LLM processes a prompt, the computational cost of the attention matrix grows quadratically with the length of the input.
It's an O of n squared complexity.
Exactly. Attackers craft highly specific, recursive queries, variable length input floods that force the model to repeatedly expand its context window.
I always like to explain it like it's not a crowd of people shouting at a server to drown it out. It's walking up to a brilliant mathematician and handing them an incredibly complex recursive logic puzzle that fries their brain and ties them up for hours.
That's a great analogy. It exhausts the GPU memory entirely. And because enterprise AI platforms bill per token or per compute cycle, a sophisticated prompt-level DOS attack can drain a monthly cloud budget in hours.
Long before a traditional security dashboard flags a network spike.
This raises an important question for defenders. If an attacker uses a distributed botnet with 10,000 constantly rotating IP addresses to submit these complex math puzzles, traditional IP-based rate limiting is entirely useless.
Because the firewall just sees a legitimate connection from a new IP and lets it through.
Exactly. Defenders have to move higher up the stack. You must implement robust, token-based rate limiting.
So you track the authentication token, the API key, or the user session, and just ignore the IP address entirely.
You have to. And you combine that with continuous resource consumption monitoring, setting strict compute quotas per user, and utilizing lightweight proxy models to analyze the mathematical complexity of an input prompt before you allow it to hit your expensive GPU cluster.
So what does this all mean? We've dismantled 9 separate avenues of attack today, and the through line is incredibly clear. Securing probabilistic AI means abandoning the medieval fortress mentality.
You cannot just build a static wall.
No. You have to implement dynamic defense in depth across the entire life cycle. You start by verifying the cryptographic supply chain. You isolate the model from your core databases by enforcing parameterized inputs on plugins.
You limit agentic workflows through strict least privilege.
You implement human-in-the-loop confidence monitoring to catch statistical hallucinations. You sanitize every single output token as if it were malware, and you shield your GPU clusters from quadratic math attacks. Mastering these specific mechanics is your key to building true enterprise resilience.
And if you're taking your SecAI Plus exam, you have to understand not just what the attack is, but the specific mechanism of how it breaks the machine.
Exactly.
I want to leave you with a final provocative thought, drawn directly from the forward-looking trends in our MITRE and OWASP sources.
Let's hear it.
We are already seeing threat actors weaponize AI to automate vulnerability discovery, crafting polymorphic prompt injections at machine speed. In response, enterprise defenders are deploying autonomous AI agents to automatically threat model architectures, deploy patches, and respond to these AI-generated attacks in real time.
Machine versus machine.
Exactly. We are rapidly approaching a future where cybersecurity is an entirely autonomous conflict, executed in milliseconds, leaving human analysts completely out of the operational loop.
Wow.
And if the attack and the defense are both driven by probabilistic statistics, who's ultimately responsible when the machine inevitably makes the wrong call?
That is a profound operational and legal dilemma. We are no longer just guarding a network. We are attempting to secure a learning, evolving entity. Thank you for joining us on this deep dive. Take these concepts, apply them to your environments, keep questioning the outputs, and we'll see you next time.